Guys, so welcome back. So today will be the last lectures of this part, basically of the geometric deep course, and I would like to talk about grids, and maybe this will relate also to the things that I expect you to know probably more than graph theory and other things, and these will be convolutions, spectral analysis. So just maybe if you can raise your hands, how many of you know what eigenvectors and eigenvalues are from algebra? Eigenvalues and eigenvectors. How many know what a Fourier transform is? Okay, convolution. Okay, good. So probably I will remind you about things that you already know, but I will again present it from the geometric perspective, so at least it will be somehow interesting, and you hopefully will also appreciate the connections to what we've seen before, and you will see that it can be derived from the same principles that we've seen so far. Basically, everything boils down to symmetry and how to use it appropriately for these constructions. So today we'll be talking about grids. Grids are special cases of graphs, right? So unlike graphs, you have more structure. We'll see that actually this structure is helpful. We'll be talking now about translational symmetry, like the permutations that we've seen before, and we'll be talking about convolutions that we'll see they will arise naturally from the translation symmetry as linear translation equivariance. And then we'll talk also about Fourier transforms which diagonalize convolution operations, and they allow us to do spectral analysis, so, which is a dual or complementary view on basically the way that we can do filtering and the way that we can do conversions. Okay, so just to convince you that grids are graphs, right? So every node in a grid can be considered as a node in the graph. So here's an example of how a grid might look like. So for simplicity of analysis, I would like to consider a grid with periodic boundary conditions, right? So a grid that is connected essentially in a circle, right? And everything wraps around. So our domain we call it Zn, right? So these are numbers between 0 and n minus 1. Everything is defined modulo n, right? So when you reach n, you basically go back to 0. And one-dimensional translations with periodic boundary conditions are called the cyclic group, right? So Zn also denotes the cyclic group. And all the arithmetics will be done modulo n, as I said, right? So the element of the group is a shift by one position, modulo n, right? So again, when I reach n, I go to 0. And this is actually a very special case where the domain itself, right, the grid with its endpoints, that we also denote by Zn, is equivalent or corresponds one-to-one to the group, right? So you can identify every element of the group, right, every translation, with a point on the domain. So this is a very lucky coincidence. This is usually not the case. So if I have time, I can say a few words about more general case of group convolutions, where the output actually lives on the group, and the group might have very different structure from the domain itself. Okay? So I will be talking mainly about one-dimensional case, but you can easily extend it to multiple dimensions, right? So how do we do it? For example, if you have a two-dimensional grid, right, or an image, you can easily write it as a tensor product or a Kronecker product, right? So what is a Kronecker product? Basically, you just multiply the two groups, right? And, for every element in one domain, you have the n elements on another domain, and you can do it in multiple dimensions as well, right? So if you apply correct periodic boundary conditions, actually it has the geometry of the torus, right? So not a two-dimensional grid, but these are technical details, right? And you can do it for any d-dimensional grid. So we define the domain. We need to define signals on our domain. So we have a space of one-dimensional signals on the grid, right, which is equivalent to our n, right? N is our number of points on the domain. We can represent them as n-dimensional vectors. And here, allow me to use just for convenience of these modulo n arithmetics, to index the elements of these vectors from 0 to n minus 1, rather than from 1 to n as we did before. Okay? And why this is very convenient to work with groups and group representations. So the way that it acts on the domain, basically it's a map between grids, right? So this thing can look as crazy as you want, right? So depending on the choice of the group. But basically we're talking about signals that live on the domain. And the map between the signals, right, which is what we call the group representation, which in our case will be just a shift matrix or a shift operator, is linear, right? So this is a typical trick that you do in mathematics in many cases. It is often called lifting. So I have something complicated that I don't like and I don't know how to deal with it, so I lift everything into some space of stuff that is easier to manipulate, which in this case is functions, right, or vectors, and it's much easier to work with vectors than with domains, right? And the domain here can be anything. It can be a graph, it can be a manifold, so this principle works in general, right? So let's see how it works. So this is my shift operator. So I have a vector, right? So these are elements, think of these as pixels of an image. I multiply it by a matrix that has looks like identity matrix, but is shifted by one position. So the result will be shifted elements of the vector by one position modulo n, right? Remember that everything is shifted by with modulo n. Now you also see that the shift operator is actually the adjacency matrix of a directed graph, the ring graph, right? You can see here. I will not talk about it today too much, but this is important because people use the adjacency matrix basically to say that this is an analogy of the shift operator on graphs. Okay? Now, specifically, we call this the left shift, right? So this is what it does to the vector. Again, everything is modulo n. And for every element of the group, you can represent it as a power of the shift matrix, right? So this is, for example, shift by two positions, right? So s squared, and in general, you can take the kth power of the matrix, and s to the power n, right, brings you back. So it's the identity. Okay? The inverse element is just the transpose of the matrix, right? So I shift left. To undo the shift left, I shift right by the same position, right? So this is the right shift, and you can see that this is the transpose. And S is also an orthogonal matrix. So S transpose S equals S transpose, right? So it's very, again, very intuitive. I shift left, I shift right, I do nothing, right? So it's equal to the identity. And what is important to know from linear algebra about orthogonal matrices, as we'll see, they have orthogonal eigenvectors. So basically, the diagonalization of these matrices gives us an orthogonal basis that we'll be calling the Fourier basis. Okay? So what do we do with two-dimensional shifts, right? So we have images of size n by m. We can represent them as n by m dimensional matrices, like this. So I can shift in the image vertically or horizontally. So I can apply the shift operator from the left to this matrix, right? And I shift up and down. Or I can apply it from the right, And here I'm shifting columns. So I'm shifting right and left, right? Alternatively, I can stack the image into a column vector, right? So basically column-wise. So this is what I denote by vec of x, right? So I get a vector of size n, m. And then I can write the shift as a Kronecker product, right? Tensor product of these shift matrices. So if you're not familiar with tensor products, I will not go into too much details, but basically it's a bigger matrix of size nm by nm, and we basically multiply an element of one matrix by an entire matrix. So it looks like a block matrix. So it looks like a big shift matrix where each of the element is a small shift matrix. Okay? So this is how two-dimensional shift can be represented with tensor products. Okay? Now, we are interested in functions of signals on grids, right? So this will be basically our design of convolutional neural networks. So we can represent them as functions that take as input vectors in Rn, right? These are signals on the grid, and then produce some kind of label. Okay? So we already seen in the previous lectures that in the geometric deep learning blueprint, it is sufficient to consider local linear invariants and equivariants, right? So they can be then combined with element-wise nonlinearities and pooling. And the linear invariants are functions that go from Rn to R, right? And linear equivariants go from Rn to Rn. So let's look at linear invariants first. So it's a function of the form, right? Because it's linear, I can write it as an inner product of x with v, right? So if you're not familiar with this notation, it's just x transpose v, right? And it should satisfy that for every shift, right? Because it's translation invariant, S to the power k x inner product with V equals to x inner product with V, right? So it's unaffected by the action of the shift. And you can easily prove that the only thing that allows me to do it is when the vector V is 1s, right? So what does it mean that I take inner product of x with vector of 1s? What does it do to the image or to the vector? So what does it produce? So how does the inner product look like? So it's basically it's the sum over the elements of x, right? So basically it's the average value, right? Up to normalization, the average pixel, right? Or the average color of the image. You see that this is not very meaningful. It loses a lot of information. So we are not interested, therefore, in linear invariants. They are very poor. They have very poor descriptive power. We are more interested in linear equivariants, right? As we've seen also in the previous lectures. And in order to be linear equivariant, it's a function of the form of this form, right? So Cx, C here is a matrix of size n by n, and it must satisfy these, right? So Cs, x equals C S Cx, right? For every x and for every k, and it is easy to show that C must satisfy the following property, right? It works both directions. It commutes with the shift operation, right? So no matter if I first apply the linear equivariant C and then I shift, or I first shift and then apply the equivariant, right? So this is the commutativity property that is important. So the question is how these matrices C under this assumption look like, right? So what can we say about these matrices? Okay, and this is what brings us to the convolution. So if I write this product, right? So what is S, C? How does this matrix look like? So I can write it element-wise, right? And this is just a notation method. So this is how I number the elements, the elements of the matrix. So I remind you that the shift operator S looks like this, right? So it's one diagonal off from the identity, right? So it has ones here and zeros everywhere else, right? So I can write it like this. I will denote it by delta, right? So delta means that it's one only when the two indices are the same, right? So when the index here I minus k plus 1 is 0 and 0 elsewhere, and the output will be C at position I plus 1j, right? So now I remind you I'm interested in the commutativity property, right? So I want SC equals to CS. I do the same thing for CS, right? So and what appears is that C at position ij minus 1 must be equal to C at position I plus 1j, right? So here they are, right? So ij minus 1, I plus 1j, right? And this must be true for every I and j modulo n, right? So it means that basically all the elements of this diagonal, right, and the modulo n element of the diagonal must be the same, right? So the conclusion from the commutativity requirement implies that all the elements on the diagonals of the matrix must be the same. So same goes here, and so on and so forth, right? So we obtain a very special matrix where the elements of the diagonals are exactly the same. So pay attention to this is very important property that instead of n squared elements, degrees of freedom, right? So in a general matrix, every element can be different. Here we have just n different elements, right? These are all these diagonals. So I can form this matrix by taking some vector of parameters, right? So a column, and then cyclically shifting it by one position at a time and appending it as columns, right? So you see how the matrix is formed. So we call these matrices circulant, and this is how they look like, right? So we have the diagonal theta 0, we have another diagonal theta 1, we have the diagonal theta n minus 1, and so on and so forth, right? And when this matrix is applied to a vector, then I can write the product in this form, right? So it's theta I minus j modulo n multiplying x, right? So we know the name of this operation. This is what we call convolution, right? So you see that linear translation equivariants are convolutions. And that was one of our prototypical examples, right, in geometric internal blueprint. So we had a grid with the translation group. We have images that live on the grid on which the group representation is the translation operator. and then convolutions are equivariant functions, right? So basically you see that it emerges itself. Basically we required that our linear equivariant must be translation equivariant, and we obtained convolution as a byproduct, right? So we derive the convolution from the considerations of symmetry, okay? So this is our story, right? That we obtain the convolutions as an application of our blueprint. Now, I already mentioned the number of degrees of freedom, but if you think that we don't have any symmetry, right? So when our group is trivial, contains just the identity element, then we don't constrain the element of our matrix, right? So it can be anything. So we have n squared degrees of freedom. On the other hand, we remember our discussion about sets, and the same thing also works for graphs. When our group is a permutation, which is a very large group, we had only 2 degrees of freedom, right? So we had a combination of the identity matrix and the matrix of ones, right? So elements on the diagonal, so which is myself and everybody else, right? So 2 degrees of freedom, so order of 1. In convolutions, we have order of n degrees of freedom, right? So we have some constraints, but they are not as restrictive as in permutations. And again, if we compare to graphs, right? So remember how the aggregation operator looked at graphs. So we could distinguish between ourselves and a multi-set of our neighbors, right? But we didn't have an ordering of the neighbors. So the neighbors came in some arbitrary order, and therefore we must treat them in the same way. Right? On the grid, on the other hand, the multi-set of neighbors is ordered. So I can consider it as a more specific function where I can distinguish between the position of my previous neighbor and my successive neighbor, right? So this is I represent here by coloring them in different ways. And if I, for example, write it as a linear aggregation, so here I can only distinguish between myself and not myself, right, my neighborhood. Here I can distinguish between individual neighbors. So if I write it as a matrix, this is how the graph convolution looks like, and this is how the standard degree convolution looks like. You see that here we have only 2 degrees of freedom. Here we have more degrees of freedom, up to n degrees of freedom, right? So this is important. Basically, as I said, the grids have they are graphs, but they have more structure, and therefore we can have more we can have more expressive functions. Okay. Now let's talk about the Fourier transform. So somehow you probably know from basic courses, right? So most of the people raise their hands saying that they know what convolution is and what the Fourier transform is. Do you know what's the relation between the two? Anyone can answer? Yeah. Yeah. So basically, Fourier in the Fourier domain, the convolution becomes a product, right? Do you know how to derive it? And actually, what is the Fourier transform? So this is what we'll try to do, right? And again, it comes from the same consideration of symmetry. So you can actually derive the Fourier transform from the same blueprint. So let me remind you a fact from linear algebra. So if we have 2 matrices, A and B, they commute, meaning that AB equals to BA, which is in general not the case, but this will be true if and only if they are jointly diagonalizable, right? It means that there exists an invertible matrix, let's call it phi, such that phi inverse A phi and phi inverse B phi are diagonal, right? So we call these matrices the matrices of eigenvectors, right? And we say that it diagonalizes the matrix. The diagonal matrix will contain on the diagonal the eigenvalues of the matrix. The eigenvalues might be different for A and B, but the eigenvectors are the same, right? So this is what we mean by being jointly diagonalizable, right? Now, our linear translation equivariance commute with the shift, right? We can look at the eigenvectors and eigenvalues of the shift matrix, right? And this will conduct us to the Fourier transform. Okay? So what we know is that S is orthogonal, right? So S transpose S or S transpose equals to I. It has an orthogonal eigendecomposition, right? Meaning that I don't actually need phi inverse. Phi inverse equals to phi transpose with complex conjugate, right? Because nobody guarantees that the eigenvectors will be real. In fact, they will not be real. They will be complex because the matrix is not symmetric. Only symmetric orthogonal matrices have real orthogonal eigenvectors. So we expect that the eigenvectors will be complex. So therefore, phi star means transpose and complex conjugate. Okay? I hope you understand what it means, right? So This is called the Hermitian or the joint matrix. Okay. So phi, basically, you can think of it as a matrix that is formed by columns of orthogonal eigenvectors, right? Meaning that phi star phi equals to phi. Right? And lambda is the matrix of corresponding eigenvalues, right? So it's a diagonal matrix. And again, because S is not symmetric, we expect complex eigenvalues and eigenvectors. They will not be real. And commuting matrices, as I said, have the same eigenvectors, but they might have different eigenvalues. Okay? So let's actually derive, it's easy to derive by hand the eigenvalues and eigenvectors of the shift matrix. So let's take some vector that is non-zero. Then for all i's, right, modulo n, Sx equals lambda x, right? And it means that I can write xi plus 1 as lambda xi, right? So because we have an explicit expression of the shift. Okay? We can do it also for s squared, right? So in this case, the eigenvalue will be lambda squared, and the shift is by 2 positions, and so on and so forth. We can also do it for n, right? And again, for n, because everything is modulo, it wraps around. So xi plus n equals to xi. Right? Because we know that this is a non-zero vector, right? At least some xk is non-zero. We have that lambda n equals to 1, right? So it means that the eigenvalues are what is called the roots of unity, right? So the solutions of this equation, and the eigenvalues look like this, right? So they look like these complex exponentials, right? So if you draw a circle in the complex plane, basically sample it at n points, this is how the eigenvalues will look like. Okay? We can plug it back into our expression and compute the entries of the eigenvectors of S, right? And this is how they look like. So they look like these complex exponentials. And here we also have normalization because we assume that the eigenvectors are normalized. So the length or the norm of the eigenvectors is 1, right? So if you put everything together, this is how this matrix phi looks like, right? And the columns of phi form an orthogonal basis that we call the Fourier basis, right? So it's hard to visualize complex functions, but basically they look like sinusoids with increasing frequency, which is a multiple of a single period, which is 2 pi over n. And historically, Fourier transform was derived, or Fourier bases were derived by Joseph Fourier for the solution of differential equations, in particular the heat equation. So it appeared in his book on the theory of heat. He was trying to solve heat equations actually for military applications, studying why the barrels of cannons exploded after certain use. And one way of thinking of the Fourier transform, so this actually came today on my Facebook timeline, but I think, well, forget about this thing. This picture is that. So you can think of a function as a superposition of sinusoids, right? So basically this function is obtained as some weighted sum of these two sines with different amplitude and different frequency that in the Fourier domain look like these deltas, right? So that's the idea. Geometrically you can think of basically what is Fourier transform. I can take a vector and represent it as a combination of orthogonal vectors, right? So these are the combination coefficients, right? So I project my vector on each of these basis vectors, right? So these are the projections. So the inner product denotes the length of the projection, so it's a number, it's a scalar. And then I multiply it by the basis vector itself, right? So I have a vector in the direction of the basis vectors of the length that corresponds to the length of the projection, right? Now, if I compute the length, right, if I combine the length of all these vectors, I get an n-dimensional version of the Pythagoras theorem. So what is Fourier transform? It's a change of the basis. I just rotate my basis in some way, right? So now instead of the trivial identity vectors, I have some other basis vectors that I call phi, right? And what we know from the properties of the Fourier transform, right, because it is orthogonal, it's an orthogonal matrix, then it preserves the inner products, right? So the inner product of the Fourier transforms equal to the inner products of the original signals. And the special case of it means that the norm of the Fourier transform equals to the norm of the original vector. So in other words, This is what we call length-preserving transformation over an isometry, right? So it doesn't change the scale of the vector; it just rotates it. Okay. Basically, what we see is that the Fourier transform, right, or what we call the discrete Fourier transform in this case, because it's applied to discrete signals, diagonalizes the shift operation, and all the matrices commuting with it, right, the linear translation equivariants, right, that we call circular matrices or convolutions. So it means that any convolution can be written like this, right? So you can write it as phi lambda phi star, and we can express convolution in the Fourier basis, right? So what is Cx? It looks like C phi star x, right? So what is phi star? Basically, I can write it like this, right? So I plug here the decomposition, the eigendecomposition of C, right? So what is phi star? X is the Fourier transform of x, right? So let's call it the Fourier transform of x hat. What can we say about phi star phi? Because of the orthogonality, it goes away. And basically what we got is exactly this. I asked this question and somebody in the audience answered. Convolution in the Fourier domain amounts to pointwise multiplication, right? So basically I can write convolution as Fourier transform multiplied by the diagonal matrix, right? Which is exactly pointwise multiplication, that's what diagonal matrix does. And then the inverse Fourier transform, right? Multiplication by phi. Okay? So convolution becomes an element-wise product, right? This is what we mean when we say that DFT diagonalizes convolution. And these matrices, phi and phi star, they have highly redundant structure, which allows to compute them instead of n squared operations, as was typically required for dense matrix multiplication, with lower complexity, n log n, right? This is possible by means of algorithms that are known as DFT, right? FFT, fast Fourier transform. They were invented in the 60s, and this is the bread and butter of modern signal processing. So you find DFT everywhere. Any filtering from your iPhone to your TV to your stereo system, basically there is some piece of hardware that implements this stuff, and this is really what makes signal processing possible. Okay. So when we move from grids to graphs, you can do exactly the same thing in a completely analogous way. We lose the DFT property because usually these matrices will not have this nice redundant structure. Okay? So the last remaining bit is actually how this lambda looks like, right? So how do the eigenvalues of C look like? And I remind you that this convolution matrix, right, or circular matrix, was constructed from circularly shifted column vectors, right? And let me express it in this way, right? So I can write C phi lambda phi for every eigenvector and eigenvalue. So I can just write it like this, right? So this was my C, this is my phi, and this is my lambda. Okay? And when I look at this product, it looks like this, right? So I can express lambda k as basically as a product of the row of this matrix and the column, which is the kth eigenvector. Okay? Now I remind you that all my arithmetic is modulo n, so I can basically I can change this element k n minus 1 to k, right? So basically I just add some number and everything is modulo n. So basically I just rewrite without changing anything these terms, so I rearrange them in this way. And basically what you see here is that it can be written as this sum. So theta L multiplied by these complex exponentials, which I hope I'm going through it a little bit fast, but if you go through these expressions again, this is just the Fourier transform of theta, right? So the conclusion is that the circular matrix can be expressed in the Fourier domain as in this way, right? So we have the Fourier transform, then the diagonal matrix that contains the Fourier transform of the vector that forms the circular matrix, and then the inverse Fourier transform, right? So basically, this we typically call the filter theta, right? And this will be the Fourier transform of the filter, and this gives us this dual picture of the relationship between convolution and Fourier transform, right? So how can I do filtering of a signal? So my signal x, I can convolve it with the filter theta, right? Or alternatively multiply by a certain matrix, right? Or do convolution between theta and x. Or in the Fourier domain, I can transform everything by the Fourier transform, right? By the DFT, multiplying by phi star. So I get the Fourier transform of x, and I get the Fourier transform of theta, and convolution becomes product, right? So this is the pointwise product between theta hat and x hat, right? So typically how signal processing works, I already design theta hat in the Fourier domain, so the filter is designed in the frequency domain. I transform the signal, right, by using a DFT, and I do it in n log n operations. I do the pointwise multiplication, it costs me n operations, and I do the inverse Fourier transform using a fast Fourier transform algorithm, which costs me n log n operations. So all the operation is done in n log n complexity, right, because we have this special redundant structure. So this is how signal processing works. And I should say that typically Fourier transform is not used in convolutional neural networks because filters are small. So if theta is large, then it makes sense to implement it with the Fourier domain because it costs you n log n rather than n squared. If the filter is of size O1, right, like 3 by 3 or something like this, then it's easier to implement it in space because then the cost will be order of n. Okay? And that's how most convolutions implemented. And that's what is implemented in convolutional neural networks. Now, one important bit, and that I will not go through it in details, but it is important, is the question of geometric stability. Now, remember that in our blueprint, we said that we compose linear equivariance with nonlinear element-wise functions, and we get nonlinear invariance, right? So what kind of functions? For example, it can be the absolute value, right? So let's look at the Fourier transform and take the absolute value, right? So this is a nonlinear translation invariant. Why? Because what the Fourier transform does, it turns shifts into complex phases, right? We've seen it already, maybe not explicitly, but basically if I shift the signal, the effect in the Fourier domain will be just multiplication by complex exponential, right? Which has a modulus of 1. So if I take the absolute value of this expression, it will be the same as the absolute value of the Fourier transform of x. So the phase disappears in absolute value. I lose some information, but I undo the effect of the shift, right? So it is very natural. The first thing that you can try, if you want to be shift invariant, take Fourier transform and take the absolute value, right? It is actually very simple and very efficient trick. Okay? The question is this invariant stable? And when I say stable, I mean the following thing. So remind you that basically what we wanted in the group invariance is that an orbit of the group is mapped to a single point, right? So all the shifts of my image must yield the same representation, right? So by design, this is how our convolutional network works, right? So I bake in my translation invariance or equivariance into the architecture. Now, this is of course an abstraction, right? So you say that I want also to be to deal with transformations that are not exact shifts, right? So how do we deal with this? So what I'm interested in, some kind of other transformation that is approximately a shift, right? So something like this. So I have maybe a little bit of a warping of an image that looks like a shift, but it's not exactly a shift, right? Or maybe a stronger warping of the image that again looks like a shift, but not exactly a shift. What I want to guarantee that if I can quantify how far my transformation is from the translation group, I want the output to be of the same order of magnitude, right? So I want some kind of continuity properties here. Okay, is it clear? That's what we call geometric stability. So we can think of shifts as a special case of more general diffeomorphic transformations, right? So you can think of it as a subgroup of a much bigger group of diffeomorphisms, right? Warpings from the one domain to another, right? So it's, let's call it tau. So it's something that can scramble pixels in crazy way, right? So if you think in discrete case, think of it as a permutation, right? So I can completely randomly shuffle the pixels in the image, and only a small subset of these shuffles will look like a shift, right? So it's a much bigger group. So the smoothness of this tau, right, of this warping, that we can measure using the function that we call the Dirichlet energy, right? You've seen it in your labs. We'll talk about it later again to understand better what it means from physics perspective. It measures how far we are from the translation, right? So what it looks like the Dirichlet energy, it's the integral over the squared norm of the gradient of tau, right? So if I have a shift, its gradient is 0, right? So the Dirichlet energy of the shift will be 0. If I have something that it looks approximately like a shift, its Dirichlet energy will be small, right? And if I have something crazy, then the initial energy will be large. So we can use this as a kind of a metric that measures the distance from the group, right? So I have now a bigger class of transformations, and I can tell how far it is from being achieved. Okay? So what I want to guarantee is that approximate invariance means that if this initial energy is small, then I want the output of my nonlinear invariant to be approximately the same, right? And here's an example. So I can construct examples of signals where this is not true, right? Where the difference is not small. So the signal that I'm constructing here will be some kind of kernel, let's say Gaussian, let's call it H, right? That is localized in space, and it's modulated by this sinusoid. So it looks like this, okay? H product with some complex exponential, okay? So it's concentrated around some frequency psi naught, right? And it has some bandwidth sigma x, right? So it will be 1 over the bandwidth of the signal in the spatial domain, right? So what happens to same way as convolution becomes product becomes convolution in the Fourier domain, right? So this is a product of two signals. It becomes convolution of the Fourier transform of H, right? Of a Gaussian, which is also a Gaussian, with 1 over sigma variance. And convolution with the Fourier transform of the sinusoid, it's just a delta function. So I have basically a window, a Gaussian block that is centered around some frequency psi naught. Okay. So let me do a version of this signal which I work, right? So my tau will be some scaling of my variable by a parameter s that we assume to be very small, right? So something that looks like this. What will be the Fourier transform? Well, it's also easy to see. It will be another blob of slightly different variance, right? 1 plus s sigma, positioned at psi naught by 1 plus s. Okay. So I can choose these parameters in my construction s and psi naught in such a way that the difference between the Fourier transform modula will be large, right? So will be of order of x. You can see it here, right? So they're completely non-overlapping. So I can choose these parameters in such a way that the difference will be large. So in other words, the relative change in my nonlinear invariant is order of 1, no matter how small is this worm, right? So how small is the initial error of this tau, the error will be order of 1, right? So it means that this invariant is unstable. So I can be unlucky that I have a modification of the signal that looks almost like a shift, but the result is drastically different, right? And we can see it here. So this is a spectrogram or a short time Fourier transform. So it's basically its frequency space plot of the original signal and its warped version. You can see that low frequencies are stable, right? So we don't have much transformation in the low frequencies, but the high frequencies are unstable. So this dilation, this warp affects them the most. So I can just decide to do low pass filtering, so I kill all the high frequencies, but this way I lose information, right? We've seen it already in the previous versions that Okaris was, the previous lecture that Okaris was showing. I can do low pass filtering on my image, right? And in some cases, if it contains sufficient information to do classification, right? So his example was pictures of mountains and seaside. But in some other cases, it's not, right? So this information is important. So the key challenge here is how to stabilize the high frequencies without losing information. And this requires multi-scale decomposition that theoretically you can explain it with wavelets, if you're familiar with it, or with scattering transforms. And this is what requires pooling in convolutional geometries. So that's why this is the missing element that we were not discussing too much about. But this is the reason, the theoretical motivation why pooling is important in convolutional geometries. Okay? So one last thing I would like to mention is how to generalize this to general groups, right? And again, we can think of convolution as a kind of sliding window, right? So if you implement it in the spatial domain, you basically have a window that you extract a patch of pixels from your image, you multiply it by some filter, you sum everything up, right? And that's the result of filtering or convolution at one position, then you move the filter to a different location. So this is how we can write it. So convolution, think of it as matching of a shifted filter. So this is the shift position, right? So the convolution at the position of the shift, you can write it as an inner product of the signal with the shifted filter, which is exactly the convolution integral, right? The convolution operation. Now, this is a very special case again on the grid. We are lucky that the domain is exactly identical to the instruction to the symmetry group, right? So we can write the convolution as an operation from the grid to the grid. But this is in general not the case, right? So the structure of the group might be very different from the structure of the domain. So if in general we think of convolution as a matching of the transformed filter, now for every element of the group, we have the corresponding group representation, which in the previous case was the shift operator, and then we transform the filter basically to a new position by the inverse of the group element. And now the convolution outputs a signal that lives on the group, right? So it goes from omega to G. And nobody guarantees whatsoever that the structure of G is the same as the structure of omega. So if you think of, for example, signals living on a sphere, right? The sphere is a two-dimensional manifold. The group that is associated with rotations on the sphere is SO3, special orthogonal group. It is a three-dimensional manifold. It has 3 degrees of freedom. On a sphere, I can rotate up and down, right? So left and right, so longitude and latitude. But I can also rotate around myself, right? So that's the 3rd degree of freedom. So the structure of the output of this conversion will be very different, right? And I don't have much time to talk about it, but basically there is a general framework that again fits into the geometric deep learning blueprint that is called irreducible representations, where you can derive a logical and self-consistent definition of what does it mean to do convolution and to do Fourier transform on a very general group. Okay? It allows to work with, for example, with spherical tensors. If you studied physics, you probably will recall orthogonal bases that are called spherical harmonics, right? So that's the analogy for your basis on the sphere. Again, I don't have time to deal with it, but it allows us to deal with signals that live on different domains like the sphere, or it allows us to deal with transformations that are not only shifts. I can do geometric architectures, convolutional neural networks that can accommodate other groups, like rotations, translations, reflections, and so on and so forth. So there is a principled blueprint to do it in this form. Okay? But we'll stop here. Any questions that you might have so far? Any questions about grids and convolutions? Was it something that you knew before? Was it something that was clear or totally not clear? Any comments? Anyone wants to say anything? Yeah, and then there is somebody in the back. Yeah. Just speak up. Yeah, maybe just shout.
Could you explain that circular matrix part of rough convolution and normal convolution? You explained that it has only the circular matrix is represented by 3 parameters only. Could you explain that part again?
Yeah, so one of the things that I repeated at least 20 times when talking about graphs is that we don't have canonical ordering of the neighbors, right? So I cannot number in a special way my first neighbor, my second neighbor, my third neighbor, and so on in the graph, right? So I need to treat them as an unordered multiset, right? Therefore, I cannot give a different coefficient to different neighbors a priori, right? So on the grid, we do have an order of the neighbors. So I can say that, for example, in one-dimensional grid, I have a neighbor on the left, I have a neighbor on the right. I can treat them differently, so they always come in this order, right? So it means that when I do convolution on the graph, I can only distinguish between myself and my neighbors, right? So if I write it as a linear aggregation, then I have one parameter for myself, right? I multiply myself with some number, and I multiply my neighbors with each of them with the same number, right? So only 2 degrees of freedom. In a classical convolution, for each neighbor, because it has a fixed position, I can assign a different number, right? So that's the difference. Other questions? Yep.
in what cases shift operators use in real life situation?
Sorry, let me get the mic because I didn't hear it at all.
What are the real life implications of shift operator? Like you said, shift to the right, shift to the left, and to the shift operator.
Yeah, so the shift operator basically it's
real life implications.
Right, so drive the convolution. So what we got from this analysis is that convolution is the linear equivariant, shift equivariant operation, right? So basically from the shift comes the convolution architecture. Okay. Might be gradually replaced by visual transformers, but basically this is what enabled, it's way more involved, but the same idea applies to rotations. Basically what you do with rotations, you need to realize that the story of Fourier transform is part of a more general thing that is called irreducible representations of the group. So for rotations, you can also derive the analogy of the Fourier basis. It's called the spherical harmonics, and basically everything else works the same. So basically, there is the same blueprint can be applied to other groups as well. And this is, for example, in physics or in chemistry, right? So if you study quantum mechanics, you probably have seen the Wigner D matrices, right, or spherical harmonics. So that's exactly the analogy of what we did here for shifts, for grids, for in spherical coordinates for rotations. Okay, so let's continue, and we'll be talking about another question.
So you said about like removing high frequency loses information, right? But you said like how to stabilize it, get the part like stabilizing.
Yeah, so I didn't go into it because otherwise I need to explain what wavelets are. But basically what you do is you do multi-resolution analysis. So you do a low pass filter and which loses information, but you don't discard high frequency information, you do the same thing to the high frequency information. So you do again a low pass approximation to it and then a high pass approximation. So this is how wavelets operate. So in convolutional neural networks, this is implemented with pooling. So you do some filtering and then you do the pooling, right? So you reduce the resolution, so you see? So the filtering part is the convolution itself, right? But the change in the resolution is the pooling, right? So what wavelets do, they do the filtering and then they basically scale the filter, right? Which is equivalent to scaling the E, right? I can explain it to you afterwards because I will need probably half an hour. So, otherwise, to explain it. Okay, so let's talk now about spectral methods. So basically, what we would like to do is to apply the same idea, but to the more general case. Okay, and a reminder. So this is what we've seen in the Euclidean case on the grid, right? So we've seen that convolutions commute. As a result, they're jointly diagonalizable, right? So they have the same eigenvectors, and we decided to pick up the shift operator whose eigenvectors happen to be the Fourier transform, right? So that's what we've seen that Fourier transform diagonalizes the convolution, and in the Fourier domain, convolution becomes a product. But there is no particular reason why we would choose the shift operator, right? So we could pick up any matrix to diagonalize. They all have the same eigenvectors, right? So we could have picked up these matrix, right? So this is also a circular matrix, also convolution. So this is a special matrix that we call the Laplacian operator, right? Now, when we are not on a grid, when we are on a graph or on some other crazy domains like manifolds, there will be, the two things will not be equivalent, right? So on a manifold, for example, we don't even have a notion of shift. So this will be really our only option, because the Laplacian operator, you can define it on a lot of crazy objects, okay? So basically what we will now be doing is we'll be repeating the same stuff that we've seen before, Fourier analysis, but now instead of the shift, we'll be considering this operator. And the reason is, again, because we can define the Laplacian as a formalized definition in all sorts of domains. It has a very clear geometric intuition that I will explain, and you've seen it already in your lab, that allows us to define it on different things. And we'll get a lot of the properties that we've seen for the classical Fourier transform on graphs, on manifolds, and other things that are related. Okay? So let's just understand what this Laplacian is. So the one-dimensional Laplacian is just second-order derivative, right? So, and what do we know about second-order derivative? If I take the complex exponentials that I've seen in my Fourier transform, right, and allow me to write here a continuous version of the Fourier transform, I take the second derivative, right? So when I differentiate complex exponential, the frequency comes out, right? The complex unit I comes out, right? So I get the same function up to frequency squared, right? So basically, these are eigenfunctions and these are the eigenvalues of the Laplacian. Okay? Another way to think of the Fourier basis, it's an orthogonal basis that minimizes the Dirichlet energy. Again, we've seen it in the lab. Basically, this is what the Dirichlet energy is, right? So we've seen it already. That's the integral of the squared norm of the gradient of the function. And the way that you can think of constructing Fourier basis, the first function, right, which is called dc, the constant vector, has Dirichlet energy 0, right? Because the gradient, of course, is 0. The second one is orthogonal to it, that has the smallest energy. So what do we know already? What would be a function that is orthogonal to a constant? It's a function whose integral is 0, right? It means that it goes up and it goes down, right? So it has positive values and it has negative values, right? So basically it will be a period of a periodic function. And it happens that the one that minimizes the Dirichlet energy is a sine or a cosine, right? Or a complex exponential, right? And we build it progressively, so to be orthogonal to a full period of a sine, you need to increase the frequency twice, right? And so on and so forth. So basically you can think of it as, if you think of the Dirichlet energy as a kind of notion of smoothness, right? So how the signal changes overall, then it's the smoothest orthogonal basis, okay? And what do we understand by smoothness is basically how far you are from your neighbors, right? How different you are from your neighbors. So what the Laplacian measures, essentially, right, and you can see it when you discretize it. So what is the discrete Laplacian when you discretize a signal on the grid is the difference between the sum of my neighbors minus myself, right, up to normalization. Okay? So the Laplacian, the geometric intuition of Laplacian is how different you are from your neighbors. That's it, that's what it measures. Okay? Now, it appears that this need to measure the difference of yourself from your neighbors is ubiquitous in physics, in mathematical physics. So more or less any physical phenomenon, pick up a differential equation that describes it, you will see the Laplacian there in some form. Okay? Let's give an example. So heat equation, right? So what is heat equation? It encodes what is known for centuries as the Newton's law of cooling. It tells us that the rate of change of temperature of an object is proportional to the difference in the temperatures between the object and its environment, right? So how do we see it in this equation? This is probably, if you study differential equations, that's probably one of the simplest differential equations that we see. So the rate of change is the temporal derivative, right? So that's instantaneously how x here denotes temperature, so how temperature changes in time, right? When I move from time t to time t plus epsilon, right? The proportion coefficient is called the diffusivity coefficient. It has some units, meters squared over second, for example. And the difference in the temperature between the object and the environment, it's our good old familiar Laplacian operator, right? So that's exactly what it measures, the difference between me and my neighbors, okay? Another example, so this is the wave equation, right? So x here denotes the position in space, right? And you can think of a wave propagation in the medium as a collection of masses connected by strings, right? So the masses move a little bit, right? And then the wave propagates, right? So what is a wave? It's basically it's a compression of the medium, right? So the particles become closer and then are pulled apart, right? So that's the physical model of the wave. So what is written here, the second order derivative, that's the acceleration, right? So what is encoded here is Newton's law, right? That tells us that the acceleration is proportional to the force. The force here is the elastic force that comes from Hooke's law. And the propagation speed here, c squared, is the proportional coefficient, right? And again, the local elastic force is the difference between myself and my neighbors, which is captured by the Laplacian, right? So again, the current motif here is that I have a Laplacian, right, that can be constructed on a grid, on a manifold, on a graph, on a point cloud, even on abstract things like metric spaces or shifts, and I don't care about how this thing looks like. The moment I can compute its eigenvectors and eigenvalues, or eigenfunctions and eigenvalues, I'm done with the Laplacian. I can forget what underlies my domain, right? And I can work only with these eigenvalues. That's the power of Fourier analysis, of spectral analysis, that I can completely abstract out and disregard the space on which these functions live, right? I can work only with these with the frequencies, okay? And I will show you now how, very briefly, of course, I will not go into all the details, how, for example, to do this analysis on manifolds. Why do I choose manifolds and not graphs? I will also show graphs. First of all, it's another creature in our geometric zoom, so it's interesting to see it. And second, it's easier to visualize, because I can visualize two-dimensional manifolds with surfaces, okay? So why manifolds in general are important? So how many of you have heard of manifolds? Anyone heard of manifolds? Yeah, very few. Well, not surprising, right? So because in undergraduate studies, unless you study some exotic mathematics, you don't hear about manifolds. Why manifolds are important in geometric ML in general, right? In applications to like, for example, genetic models, is that they allow to model continuous symmetries, what we call Lie groups, right? So Lie groups are manifolds. I will not be talking about it. We don't use it here. But when you talk about three-dimensional objects, like applications in computer vision and graphics, so they are manifolds. So manifolds allow to think of the object as only its external surface, right? Which is a two-dimensional manifold, technically speaking. When you, for example, do drug design, right? So when you want to understand how proteins fold and how they interact with each other, the folding itself doesn't really matter for the interaction of proteins. So what matters is how the molecule looks externally, right? The molecular surface, or at least it's one way of abstracting out all these details. So we can actually use these methods that I will only allude to design new molecules. We can test them in the lab. I hope I will have time to also show you some examples. So this thing work and potentially can be used for new drug design, right? So going from these very abstract notions of differential geometry to actual stuff that we can test in the lab tube and potentially cure patients. Okay? So on manifolds, again, I will not be going into the details. We also can think of them from the geometric perspective, what kind of symmetries we have. And the symmetries that we have on manifolds are of two types. We have local symmetries, which is the change of the basis, right? So the local choice of the basis. We don't have a global system of coordinates on manifolds. I will show you immediately why. And then the global symmetries, which are called isometries. So deformations that do not change what is called the metric properties of the manifold. Basically, if you live on the manifold, you don't perceive any difference, right? So let's make some definitions. So what are manifolds? And you can study an entire course in differential geometry, but basically, technically speaking, these are topological spaces. A topological space is roughly a space where you have a notion of who is your neighbor, but not how far it is, and not any notion of angles and distances, right? So graphs, for example, are topological objects. I can define my neighbors, but I don't have any other geometric information unless they provide some extra stuff. Okay? So when they say that the manifold is smooth or differentiable, it means that the transition between these local neighborhoods, that is called charts, are smooth, right? So they're differentiable, they have differentiable inverses, and so on. And what is important that topologically these local neighborhoods are equivalent to some S-dimensional Euclidean space, right? When we say that this is an S-dimensional manifold. And the way to think of it, so this is a two-dimensional manifold, the surface, right? Locally, it looks like a plane, right? So when you sit in this room and you look outside of your window, you don't see that the Earth is a sphere, right? You see that it's flat, locally, right? If you zoom out, if you fly into space, of course, you will see that it's curved, right? But locally, in some neighborhood of yourself, you will see that it's flat, right? So you can identify it in the sense of topological homeomorphism with the Euclidean plane, right? So we call it the tangent plane, and then the collection of all the tangent planes is called the tangent bundle, right? So that's how you work with manifolds. You don't have a global system of coordinates, you have a local system of coordinates in each of these tangent spaces. Okay? Now, remember, so this is just the domain. We also have signals on the domain. So we might have two types of signals on the manifold. We might have scalar fields, right, or scalar signals. It's just a real function that from the manifold to the real space, right? So think of temperature. So at every point of my surface, I have a different value of the temperature, right? So I can represent it by this color, right? So basically every point is colored in a different way. We can also think of vector fields. So these are functions from the manifold to the tangent bundle, right? So basically what vector fields represent is some kind of flow, right? So at every point I describe a direction in which some stuff flows, right? So technically speaking, these are tangent vectors, so these are vectors that live in these tangent spaces, right, or live on the tangent bundle, and we can deal with them as inner product spaces or Hilbert spaces, so I can write appropriately defined inner products for the scalar and the vector fields, right? Now, once I have functions, I can also define derivatives, right, or differential operators, so I can define the direction of the steepest increase or decrease of a function at some point, right? So the vector that points in this direction is called the gradient, right? At that point, and if I look at it as an operator, then it's basically an operator. It's some mathematical black box that takes us from scalar fields to vector fields, right? So if I have, for example, a distribution of temperature on the manifold, then at every point I can see in which direction the temperature changes the most, right? And the arrows that point in these directions will form a vector field, right? So the gradient takes me from scalar fields to vector fields, right? I guess you know it probably from standard multidimensional calculus. Now I can do the opposite, right? So if I give you a vector field, I can take around every point in a small sphere and see how much field flows in and out, right? So this is called the divergence. It is the opposite operator to the gradient, or formally it is called the adjoint operator. And basically it means that basically a joint is defined like this, right? So you can exchange the two operators, and of course pay attention that the inner product here is different. So this is inner product on vector fields, this is inner product on scalar fields. Okay? Why I'm telling you all this? Because we can define now the Laplacian operator, or what differential geometers call the Laplace-Beltrami operator, as the divergence of the gradient, right? So basically, the gradient takes you from scalar fields to vector fields. The divergence takes you back, and what together it does, again, it's the local difference between the function at the point and the average neighborhood value. When the neighborhood is defined appropriately in the sense of differential geometry using these operators. Okay. What is important that it's intrinsic, meaning that it's totally defined through the Riemannian metric of the manifold. It is self-adjoint, which is a fancy way of saying that it's symmetric, right, if we represent it as a matrix. And we know that symmetric matrices, right, or self-adjoint operators have real eigenvalues and orthogonal eigenfunctions, right? Or symmetric matrices have real eigenvectors, real eigenvalues and orthogonal eigenvectors, okay? So this operator is called after Laplace and Beltrami, and we can again define it on many different things. We can define it on meshes, right? So we talked about graphs, we talked about high-dimensional structures. So if I give you this horse shape, I can think of basically sampling some continuous surface at some points, right, that become nodes of the graph, and I connect them locally by edges. So that will be a graph, but it loses the two-dimensional information, right? So a high-dimensional object, topological object, is called a triangular mesh, which also has additional structures that are called faces, right, or triangles. So if node is a zero-dimensional object, right, point, then an edge is a one-dimensional object, so it's pairs of points. Here it's a triplet of points defined in such a way that the edges of the face are edges in the graph, right? And the vertices of the face are the vertices of the graph. And of course, we need to make some extra assumptions. If we want the mesh to properly discretize the manifold, it has to satisfy some additional properties, right? That doesn't matter. Basically, the bottom line of this discussion is that I can define a Laplacian on the mesh exactly the same way as I can define it on graphs, right? So it's basically it's the difference between myself and my neighbors, right? Up to some weights. So right. So this is the average of my neighborhood, and this is myself. Okay. So I can write it when I write it on a computer, I can write it as an n by n matrix, and it looks like this. D is the degree matrix, right? So that's what it is. W is the matrix of weights, of basically corresponding to my neighbors. And it is typically sparse, right? So it has the number of non-zeros is as the number of edges in the graph, right? And in the case of meshes, it's all of n non-zero, right? So you see that I can build Laplacians on all different things, but I don't really care about the Laplacian. What I care is I will then be doing its eigendecomposition, so I compute its eigenvectors and eigenvalues, and then whether it's a mesh, whether it's a point cloud, whether it's a manifold, whether it's a graph, it all looks the same, right? So what we are interested in is the Laplacian spectrum. And let's do the following experiment, so I hope you will be able to hear it. So what I will do is, we will take a plate, a metal plate, put some grains of sand in it, and apply vibrations of different frequency. Like this. So you see that at some frequencies these patterns form, right? So you've seen at some frequencies you've seen certain patterns forming, and basically this experiment was first described by Ernst Chladni. He tried to understand why certain musical instruments sound better than others, right? So why a Stradivari violin sounds sublime and some crappy violin that my son plays doesn't sound well, right? So it might be also the depends on the player, but basically he tried to visualize the sound. And at that time, he didn't understand really. We didn't understand what the wave phenomena. So this realization came significantly later. So he was touring different royal courthouses in Europe, and Napoleon even promised to give an award to somebody who explains what is seen here. But of course, nowadays we understand what is happening here. Napoleon is of course not around, so we cannot claim the award. But basically, what we see here is the wave equation that describes propagation of waves on this object, on this plate, and how we solve the wave equation, right? So I remind you, probably you've seen it in basic course in PDEs. We do separation of variables. So we assume that the solution, right, which has two variables, the position and the time, I can write it as a product of a function that depends only on the space and only on the time. Okay? If I plug it into the equation, right, so I have phi u, second derivative of tau, equals to the Laplacian of phi multiplied by tau, right? So let me rearrange it, so I will divide everything by tau and phi, right? So I have these ratios that are equal, and this is true for every t and every u. So let's call it lambda, right? So it's constant. And I call this constant by a name. I call it lambda, and unsurprisingly, I hope you will see why we call it lambda. Okay? So the spatial part of the solution, this one, satisfies what physicists call the Helmholtz equation that looks like this. Laplacian of phi equals to lambda phi, right? So basically, phi, the eigenvectors of the Laplacian are the vibration modes, and lambda are the vibration frequencies. So what you see in the experiment that Chladni did is zero crossings of these functions, right? So the grain of sand do not jump at some positions, and that's exactly where the function, the eigenfunction is zero. So at some frequencies that are these lambdas, you will see the eigenvectors of the Laplacian, you will see there as zero crossings, right? So these are called stationary waves in physics. So if you look at the manifold, right? So a plate is just an example for manifold, but we can consider general manifolds. The Laplacian has a countable spectrum, so it is discrete, it doesn't accumulate except at the infinity if the manifold is compact, right? So every object that we can consider in real life are compact. And you see also that the Laplacian eigenvalues contain some information about the manifold, right? So we can see it from the heat trace expansion, so we can recover quantities like the area, the Euler characteristic, or the genus. The question is whether we can recover the entire manifold from its spectrum, right? So whether we can recover the measure. And this is a question of whether isometry is equivalent to isospectrality, right? When I say that something is isospectral, it means that its Laplacian has the same eigenvalues. When I say something is isometric, it's roughly in geometric terms to say that the manifolds are the same, right? Up to some deformation that doesn't change their internal properties. So it is obvious in one direction, right? So if I have two equivalent manifolds, then the Laplacians will have the same eigenvalues. But the opposite direction is not clear, and it was poetically put by Mark Katz, who asked the question, can you hear the shape of the drum, right? Because the lambdas, right, the eigenvalues have this acoustic interpretation. Can you actually hear the shape of the manifold, right? It's metric. And if you think of, for example, the bell foundries, right? So since Middle Ages in Europe, people were producing bells, so they could actually, from the sound of the bell, they could know their shape, right? So they could know, for example, whether there is a crack. And the answer to this question is unfortunately no, so you cannot hear the shape of the drum, and you show it by counterexample that was shown in the 90s by Caroline Gordon. So she showed examples of isospectral but not isometric manifolds, and actually there are continuous deformations from continuous mechanisms of such manifolds. So this is in theory, but in practice, with some regularization, you can actually hear the shape of the drum, right? So you can reconstruct the shape from the spectrum. And here is an example. So we call this isospectralization. That was a cute paper that a postdoc of mine, who is now a professor in Sapienza in Rome, basically that you can recover from the spectrum the shape, but you do it by optimizing the spectrum, basically optimizing the coordinates of the shape in such a way that the eigenvalues align with some reference spectrum. Okay? So why I'm telling you this, we want to design a non-Euclidean version of the Fourier transform, right? We can do it on manifolds, we can do it on graphs. Basically, these eigenfunctions of the Laplacian are the analogy of the Fourier basis. We know that they're orthogonal, right? We also, in case of manifolds, know that they're intrinsic, so they survive deformations, right? And we can define Fourier transform in this way, right? Just as inner products of our signal with the basis functions, right? Which is given in the case of manifolds by integral, in the discrete case by sum. And the inverse Fourier transform is exactly what we've seen before, right? So these are the Fourier coefficients multiplied by the basis functions, right? Again, if I write it as a matrix, it comes from the orthogonality of the Fourier transform. So basically, it allows us to decompose scalar fields in orthogonal basis. Now, pay attention that the frequency now is one-dimensional. We don't have any notion of direction. And again, what is important that we can work only with Fourier coefficients, so we can forget about the underlying space, right? About the manifold. So again, I construct the Laplacian and then I forget about where it comes from. I just look at the phi and lambda. Okay? So remember that we had convolution as well, right? What is a convolution? So how do we write convolution? I can define convolution now, before it was a property, I can define convolution as the product of Fourier transforms, right? So here is the product of the Fourier transforms, and this is the inverse Fourier transform, right? So this is how I can define convolution. Unfortunately, we don't have f of t now, so we have, if we implement this matrix multiplication, it will cost us n squared operations. And the filter is not necessarily localized in space, and the filter, because of the one-dimensional frequency, is isotropic, right? So we don't have any notion of direction, so the filters look like this. Okay? Now, it is in principle isometry invariance, but in practice it's unstable under deformations, exactly because of this problem that the high frequencies are unstable, right? So the low frequencies are usually stable, the high frequencies are unstable. So this is how it looks like, right? So this is, I can write the filter as some transfer function as a function of lambda, right? So lambda is a frequency, this is called in harmonic analysis the transfer function, instead of implementing it as just a set of coefficients. And you can see here, so in this case, I have a galloping horse, so it is deforming the eigenvalues and the eigenfunctions remain approximately the same, and you can see that the filter which I multiplied by a delta function to show it is a kernel looks very stable. Okay? So what you also see is that the filter, right? So this is the filter. I can write it as an integral with some kernel. It is not shift invariant, right? We don't have a notion of shift on manifolds or on graphs, and therefore it's position dependent, right? So you can see that if I localize it at different points, point U and another point U, it will look different. Okay? So it's position dependent. Now, let's do the sanity check. So if I take the standard convolution in the Euclidean case, right, so my phi the eigenfunctions will be just the complex exponentials, and in the case of complex exponentials, we have the associativity property. So now it becomes a function not of u and v independently, but of the difference between u and v, right? So this is gain a convolution over a circle of matrix. So back to graphs, right? So why did I tell you this story? So we've seen graph neural networks. We can talk about convolutions on graphs as well. So again, we need for this purpose the graph of Laplacian. So you've seen it in your labs again. So this is how it is defined, right? So it's weighted average of the differences between the features in node u and node v, right? So this is the analogy of the gradient operator, and this is the analogy of the divergence operator, right? So the gradient takes you from the signal that lives on the nodes to a signal that lives on the edges, right? So that's the analogy of the vector field. And then the divergence collects all the information that lives on the edges that share a node and gives you a node-wise signal. Okay, but if I just manipulate this formula slightly, I can write it as the difference between myself and my neighbors, right? So this is xu, right? So that's my own feature, right? Xu here. And this is the average of the neighbors, right? So remember the way that we have a generic form of aggregation on of features in the neighborhood of the graph, so that's exactly how it looks like. So it's a special way of linearly aggregating the neighbors in a permutation invariant way. Why permutation invariant? Because the sum is permutation invariant. Okay? So this is our linear equivariant function that looks like this, delta x. Okay? And that's why we call it convolutional flavor, right? So because it's exactly what gives us convolution in the Euclidean case. Right? And that's the linear aggregation that we obtain with the graph of Laplacian. So this was actually some of the earliest GNN architectures were based on the notion of the graph Fourier transform. So you can find some seminal papers in this field from the group of Pierre van der Geijns and PFL in particular about the field of signal processing on graphs that appeared in 2013. So that roughly coincided with the deep learning revolution that happened, and this gave also inspiration to the design of the convolution architectures that just try to implement convolution on graphs using the non-Euclidean signal processing stuff. It was the revival of the interest in graph neural networks. As I said, it has high complexity. It's not used in practice. It's good to derive formula, or it was the initial set of works that now have been substituted by other ways. And there are many ways of designing these filters. Right, so this is how you do the graph Fourier transform. It's exactly the same as we did with the manifold, right? So you take the graph of Laplacian, you compute its eigendecomposition, right? So you have orthogonal eigenvectors. You multiply by this matrix with complexity of order of n squared, right? Because you don't have the fast Fourier transform algorithm. You compute the same way the inverse graph Fourier transform, and the spectral convolution is defined as element-wise product of the Fourier transforms. So ChebNet, which was one of the early algorithms, and the GCN, the graph convolutional network of Kipf and Welling, was a simplification of this method. Basically applies a polynomial transfer function to the Laplacian spectrum. What is important about this way of doing it is that you don't need to explicitly compute the eigendecomposition of the Laplacian. You don't need to compute these eigenvectors and eigenvalues. You can just, it boils down to taking the powers of the Laplacian and combining them with some learnable coefficients. It is also efficient, right? So it's approximately order of n, and it's stable under graph deformation. What you can also see that it boils down essentially to simple local averaging, right? So that's the convolutional flavor of GNNs, and therefore the spectral and the spatial view of GNNs is exactly the same way as we have it on the grid, right? So the analogy of doing convolution in the spatial domain and doing it in the spectral domain, they're related by the Fourier transform. So here it's exactly the same thing, right? So the convolutional flavor of GNNs, you can implement them as averaging operators in the spatial domain on the graph, or as these kind of transfer functions on the spectrum of the graph of Bronstein, right? The two views are the same. So if some folklore says that there are spectral methods and there are spatial methods, essentially they're the same method. Okay, any questions?
I have a question there. I have LiDAR. While scanning through the LiDAR, the result is in point cloud, which is not particularly useful. I will transform it to the mesh, which will be more useful geometrically, as we know that. And we know that manifold is exotic. We can assume set as the continuous surface, accept the node and face. It will be more useful, as I have learned in your paper that the symmetrical complex is used. Can you explain it?
Yeah. So basically the question is between, basically if you have different, let's say, different levels of granularity, right, or different level of information. So you can think of geometric objects as just sets of points, right, point clouds. You can think of them as graphs. You can think of them as simplicial complexes, right, which is meshes. So of course the mesh contains a lot more information. It is also geometrically more correct. Now, it is difficult to work with meshes, especially when you want to generate things, right? So it's difficult to generate meshes that are topologically correct, that are manifold meshes. So what turns out in practice is that a point cloud, when you also have the normals oriented point cloud, it is, if it's sufficiently dense, and it's as good as anything else. So people also use implicit representation for geometric objects. So the choice of the particular choice of the representation is really application dependent. And it's much easier to work with sets than with meshes. Now, people who do more complicated things in computer graphics, for example, you want to solve some differential equations on meshes, there you need to work very carefully, for example, to guarantee that you have conservation laws, right, that things don't fall apart. So there it's actually very important to use the mesh and discretize correctly all the differential calculus. So this stuff exists from the 90s. Discrete exterior calculus is heavily used, so it's beautiful discrete differential geometry. In practice, for learning applications like, for example, shape classification, shape segmentation, you really don't need it in most cases. So we had a hybrid approach that we called dynamic graph convolutional networks with Justin Solomon from MIT. It's actually a very popular paper where we look at point cloud with some local connectivity that is basically a learnable graph that is constructed on the fly. So it gives you an idea about local geometry, but it doesn't give you the full-fledged representation of the geometry as a mesh. Right? So I hope it answers your question.
Hi, I'm Sadhana Panthi. So this might be basic, but I'm still confused regarding the clear difference between graphs and manifolds. What changes might happen if we use manifolds instead of graph? And since we're discussing regarding the graph neural networks, I wanted to know if we use manifolds instead of graph, is there something like manifolds neural network, or is it comes under graph neural networks only?
Yeah, so first of all, there are manifold graph neural networks, and again, I didn't have time to explain it. Basically, what they do, they work with local coordinates, and basically, they design a different type of convolution that is, it's more expressive because here everything is isotropic, right? You don't have a notion of direction. If you work with a manifold, you must work locally in the tangent space, but then you have a notion of direction. The problem there is that you have an arbitrary set of coordinates at every point, right? So I don't have a canonical global set of frames. I need to make sure that my frames are equivariant, basically my filter is equivariant to the transformation of the local reference frame, of the local system of coordinates. So this is called gauge equivariant convolutional neural networks. Gauge here refers to the choice of this local coordinate frame on the tangent bundle. And it's a beautiful theory, so it was developed by Taco Cohen and Max Welling. I would need a few hours to be able to explain it, so that's why I didn't include it. So basically that part exists on its own, and it's beautiful. So when it comes to the spectral representation, and this is the advantage, you've seen how the Laplacian looks on the manifold, right? It's the same as the graph Laplacian. So the weights are different, they account for the geometry of the manifold, but once you computed the operator, it has exactly the same structure as the graph Laplacian. Once you do its eigenvectors and eigenvalues, you can forget about that came from a manifold and not from a graph. Okay, so in terms of the structure of the architecture of these spectral graph neural networks, manifold or graph, it's exactly the same thing.
So does that mean in case of spectral there comes the difference, or is it the exact same?
So the difference comes from the fact that you throw out some structures that exist on manifolds, right? And that's the notion of local direction. So you basically you lose some ability, some expressive power in this way. But what you gain is something that is more universal, right?
Okay, thank you.
I think this question.
You showed like some signals on the manifold were unstable. Like I was wondering why.
Yeah, so it's not the signals on the manifold; it's the filtering on the manifold, right? So I glossed through it, but this is actually important. So let's say I do a filter that looks like this. So I have a signal, right? So just ones and zeros with these blobs, and I do edge detecting filter, right? So how do I do filtering on the manifold? So I have the coefficients of the filter. That's the Fourier transform of my signal. That's the Fourier basis, right? So the problem is that when I take a different manifold, right, which is even an approximate isometry of this one, the filter coefficients do not speak in the same language. So by eigenfunctions, for example, I define up to a sign, right? So there is no way whatsoever to guarantee that even if I take the same shape and I compute the eigendecomposition of the Laplacian, once again, this phi will not come with a different sign, right? And more generally, especially at high frequencies where the numerical errors are higher, there might be some transformations, rotations for them, right? So if you have multiplicity of the eigenvalues. So bottom line, what happens is that if I give you another domain, right, let's call it omega wave, and it has a different basis, slightly different, the same coefficients will produce a completely different result, right? So that's why we insisted on using the transfer function that can be parameterized, for example, as a polynomial rather than using here fixed coefficients. Okay, so this is something that depends on lambda, on the frequency, rather than putting here some fixed coefficient. Okay? So that was the main reason.
So just further, so like 2 is the same Horst, but it's just a different morphism, right? A different image.
So it's an approximate isometry. So there are, for measures, actually, there are almost no true isometries. So it inevitably deforms the metric. So the Laplacian is slightly different. And this error is manifested mostly in the high frequencies. So the noise, like in the case of the Fourier invariant, comes mostly from high frequencies. Low pass filters are stable, like heat kernels. They're stable. Yeah. There is a question. Sorry, I didn't.
So like in manifold, like they change the high dimensional data to low dimensional data, like they remove some features. Like they don't need all the features and but some are necessary, right? Like in manifold.
You mean here, in this example?
Not in this example. Like if we have passed it through manifold, they will remove some, they will reduce it to low dimensional data.
Well, this is something different, right? So you're probably talking about manifold hypothesis. Meaning that, for example, when you have images that live in a million-dimensional space, in practice their intrinsic dimensionality is much lower. So the term manifold here is used in a very loose way, right? Because it's not exactly a manifold from differential geometric perspective. It's something that has low dimensional, and maybe you can think of that it's roughly sampled from a manifold. But even the dimensionality at different points might be different, right? So it's not a true manifold, but it's a good manifold.
Just to ask the question that was asked previously, like you talked about in higher frequencies, the there is no stability or we can't get stable? Is it because that in higher frequencies the changes are rapid, so we cannot get the notion of stability?
Yeah, so it's multiple things. So it's numerical instabilities, and it's also because the changes are more rapid. Yeah, you can think of it this way. So in the Fourier basis, basically, higher eigenvectors have more zero crossings, so you get a lot more differences. Okay, let's talk about applications. Well, I should say that I didn't really prepare for this, so I will just show you nice pictures. Okay, so we can also make it more interactive. So basically, why we bother, right? Why we bother talking about all this stuff? So first of all, and I think multiple times I was asked, how do you use this or that mathematical object in practice, right? So in some cases you don't use it in practice, right? I think somebody asked, how do you use the shift operator in practice? You use it to divide things, right? So from the shift operator, for example, we got the convolution operation, which is used in convolutional neural networks, and then convolutional neural networks, I think I don't need to tell you how they're used in practice. They created multi-billion industries, now bread and butter in computer vision. For some other things, right, so for example, we talked about graph neural networks. These are very useful, right? So in many cases, the data that is produced by some business naturally comes, or some physical phenomenon, naturally comes in the form of a graph, right? So if you think of different e-commerce applications or social networks, basically these are graphs, right? So social network can be described as a graph that relates different users, right? So we have multiple types of graphs, for example, who follows whom, right? So this is a directed graph, who messages whom, right? So a lot of this stuff. So in particular, what is used in different applications, right? So now you find it everywhere, from Google to Facebook to Twitter to Amazon, is recommender systems. So for example, if a user buys certain products, you would like to be able to suggest to the user what to buy, right? Or suggest the user to follow on a social network, or suggest a video to watch on YouTube. So all of them use some form of graph learning. And it's basically it's a problem that we didn't talk about too much, is the problem of link prediction. So you want to represent the graph typically in some vector space, so you want to embed the graph, you work with nodes as vectors, and then you can try to suggest, to recommend links based, for example, on proximity or similarity of the node embeddings, right? So this is very useful and very practical. Now, another application that is important for social media is all the story of disinformation. So when we worked on this, that was prior to the presidential elections, the first ones in the US when Donald Trump was elected for the first time. So people were concerned with a lot of what was called fake news or misinformation, and there was a lot of computational sociology studies that tried to look at how these kind of fake news spread over social networks to try to be able to identify them. So, and it was, there were some patterns that were detected, for example, that this kind of misinformation doesn't spread organically, so it spreads differently. So we try to use graph neural networks to be able to classify it automatically. So we have a startup company called Fabular that Twitter, at that time was still Twitter, a public company, acquired in 2019. So Federico was actually one of the co-founders. You can see him here, along with some other people. So well, now Twitter, of course, is in different hands and a very different company from what it used to be. But that was one successful example of the use of graph neural networks for commercial application in social media. So we talked about manifolds, right? So you can ask why this exotic stuff is interesting. So manifolds are used to model shapes, right? So something like this, like computer graphics. So this is special effects that you can find in movies, right? So computer graphics. So this is an avatar that is generated in real time from the face of an actor that is acting in front of a three-dimensional sensor. So that was a Swiss company called called Phase Shift. So it was acquired by Apple. So if you use an Apple iPhone, well, I don't know what the current versions, but it has a tiny three-dimensional sensor here at the top. And basically it scans your face, it gets a three-dimensional structure, and then it basically it allows to do these kind of things. So I think an emoji, this is how Apple calls it, so that's powered by this technology. So three-dimensional sensors were actually very popular in the last decade. So I myself was doing it still as a master's and a PhD student, so we're working on three-dimensional face recognition. Sorry, and had to build our own three-dimensional sensor because they didn't exist about 20 years ago. So this is an example of an FPGA prototype. So in this case, it has hand tracking. So it's an active sensor, so it illuminates with infrared radiation the hand, and then basically reads out these patterns. So it's called coded light or structured light, and can measure the distance or the angle from the sensor. So this was another company, another startup I was involved in, called Envision. It was acquired by Intel in 2012, and Intel used this technology. It was called RealSense. It was using it for basically with the idea that you can interact with your computer with gestures, with hands. So this was a commercial that was, you can recognize the guy from Big Bang Theory. I'm always forgetting what's his real name is. And basically he showcases here some of the applications. So this was, I would say, an interesting example of how fast the field moves and how it's an ungrateful job to make predictions. So at that time, well, 12 years ago approximately, I was saying that in order to do this kind of hand tracking and pose estimation and gesture estimation, you must have a three-dimensional sensor because the two-dimensional image, it's too difficult to work with this input. But just a few years afterwards, one of my PhD students, Dominique Coulon, was already showing that you can take a standard two-dimensional input and use geometric deep learning just as a decoder. So the encoder is a standard convolutional neural network, again, part of our geometric deep learning blueprint, but the decoder is a special mesh CNN, so somebody asked me about manifold convolutional neural networks, so we use exactly these sort of things with local system of coordinates. It allowed to build full avatars, so he was working mainly on hands, but the extension was full body avatars, faster than real time on a standard iPhone with this technology. So basically from two-dimensional video input, you build this three-dimensional avatar. It was a collaboration with a company called Real AI that was founded by a colleague and a friend of mine, Yasos Kokinos. So they were acquired by Snap. And I guess if you're a user of Snap, you might have seen this technology in one of their applications. So I don't claim much credit to this. So I was one of the investors in the company, and basically my student was working on this. So another application. So if we talk about graph neural networks, you might recognize this picture, right? So this is probably one of the biggest and most complex and most expensive machines that were built by humankind. So I'm talking about the LHC, the Large Hadron Collider. So this is one of its detectors. Basically what it does, it accelerates particles to almost the speed of light and then bangs them together. And each bang produces a shower of 1,000 other particles that are detected by this detector. And this is how these events look like. So we have millions or billions of these events per second at the LHC. And this is how high energy physicists understand how the universe works, right? So this is how the Higgs boson that was theoretically predicted in the 70s was experimentally confirmed. So this is, I think, actually the event that's described here is the Higgs decay. So that was one of the events that was used for experimental confirmation of these particles. So graph neural networks are now used by high energy physicists to classify these kind of events. Basically, the problem with these accelerators, they collect petabytes of data. So most of these events are not interesting. They don't contain any interesting physics. So you want to do very quickly to filter out 99.9% of these collisions, and you need to do it in real time because there are millions of these per second. And they develop special hardware, and graph neural networks appear to be very natural way of describing these events, as well as efficient way of being implemented in browser. So here's another thing. So this is another high energy physical experiment. So this is literally sits on the South Pole. And if you think of what is this small construction, this is an example of an expression, the tip of the iceberg, because the detector itself is actually carved into a cubic kilometer of ice on the South Pole. Basically, this is a neutrino observatory called the Ice Cube. As you probably know, neutrinos are particles that almost never interact with matter, but sometimes they do, and that's why you need such a big detector. So from time to time, a neutrino flies from some distant astrophysical sources, and it interacts with the water or the hydrogen atoms in the ice, and it produces basically a flash of light that is picked up by photomultipliers, by the detectors here, and that's how this event looks like. So again, with Federico, we had one of the first papers that used graph neural networks to do event classification in the Ice Cube neutrino observatory. Basically, this kind of what is called multi-messenger astronomy that integrates data from different sources. So nowadays we can measure gravitational waves with LIGO experiment. We can measure neutrino with Ice Cube. So all these gives different modalities or different flavors on the same thing, and this is potentially will lead to groundbreaking discoveries in astrophysics, trying to understand how the universe looks like after the Big Bang. So graph neural networks are also very popular as kind of backbone for different types of simulations, right? So for example, computational fluid dynamics, right? So these are complicated equations, Navier-Stokes equations. You can replace them with learnable architectures that are implemented as graph neural networks that can make these simulations significantly faster and significantly more accurate. And probably one of the best examples, this is already an old story, so that appeared on the cover, I think, of Science. This is DeepMind's work called GraphCast, which forecasts weather significantly more accurately and faster than traditional methods. Again, it's based on graph neural networks and special geometric architectures. So talking about molecules, so this is what I'm working on with my collaborators. Basically, all the business of drug design, right? So how do drugs work? So most drugs look like this. So you have some target, which is a protein molecule in your body, right? So the protein looks like this. So you can think of it as a blob. That you can think of it as a geometric surface, right? That's why we need geometric methods. And it has some kind of pockets, right? So and the pockets is where other stuff binds to it. So for example, this is how the coffee drinking process looks like. So when you drink coffee, there is a protein that is called an adenosine receptor in your brain. So it looks like this, but of course much smaller. And then the caffeine molecule, right? So it's what I'm showing here is not exactly caffeine, so it's same chemical class, but let's think of it as caffeine. So it's a small molecule that penetrates the blood-brain barrier, enters into your brain and binds to this receptor. And this triggers some chemical reaction that makes you feel awake, happy, euphoric, whatever kind of drugs you take, right? But basically, this is this kind of mechanism. If you identify some receptor, right, so some target that you need to bind to, you can disrupt certain processes that are responsible for diseases, and therefore drug design tries to find a molecule that binds to this particular target and to nothing else, right? So it doesn't have any side effects. And many targets do not look like this, so it is lucky that you have a pocket that can be drugged by a small molecule that can enter into it. Many of the interfaces, right, many of the targets are completely flat. So this is an important oncological target. It's called program death ligand 1. So this is a protein that is responsible for a kind of friend and foe mechanism in our body. So we have immune system, cells that kill constantly all the stuff that is not supposed to be there, including malignant cells, including cancer. So the way that the immune system doesn't kill its own cells is the presence of these proteins that basically inhibit the function of the immune system, and therefore the cell is not destroyed. So it appears that some cancers do express these proteins and they are able to evade the normal functioning of the immune system. So then the tumor grows, right, and affected by the immune cells, and then we have a problem, right? Basically we have cancer. So the idea of immunotherapy is to block one of these proteins, it's either PD-1 or PD-L1. They work in a complex by a molecule that is designed, right? And this molecule is protein. So instead of binding PD-1 to PD-L1, you bind it to some new molecule. Could be an antibody, could be a peptide that is introduced artificially into your body, and then basically the immune system takes control back and kills the cancer in the normal way. So the way to think of it is kind of a lock and a key, right? So if you think of the lock with these knobs and its unique configuration that accepts only one key as a metaphor for a protein and a molecule that will be unique and will bind to it, so that's what drug design is after, right? So finding a key for a particular lock. And proteins, you can think of them as, basically these are polymers, right? So they're composed, as you probably know, of sequences of amino acids. So it's a chain of amino acids that under the influence of electrostatic forces folds into complicated shapes that look like this, right? So this secondary and tertiary structure. And what DeepMind was trying to do with AlphaFold is to predict to go from here to here, to go from the amino acid sequence to the three-dimensional structure. And it was an important problem, so that's why the Nobel Prize was given this year for solving it. It was long-standing problem in structural biology for over 50 years. But when you try to design drugs, you actually are interested in some sense in the inverse process, right? So you want to find a sequence of amino acids that will fold into something that will bind to something, right? And that's what we are trying to do with geometric deep learning. So I'm working with a group in Switzerland at the PFL, or basically they're structural biologists. They build these proteins and they can design proteins using geometric deep learning methods to bind to particular targets. So I mentioned PD-L1, so these are a few proteins that we designed and actually tested in the lab that bind to these proteins. So it was a paper that appeared on the cover of Nature Methods. We've had some other follow-up work. For example, this is a design of a binder for the spike protein of the SARS-CoV-2 virus, so the one that was terrorizing us for many years with the COVID disease. And you can see here that actually the design is efficient against different variants of basically different mutations of the virus that result in slightly different structures in the spike protein. But we can also compare it to the clinically approved drug from AstraZeneca, basically a cocktail of antibodies that were not designed, but they were developed by directed evolution. So here, this is a purely computational design of a protein that binds not as efficiently, but in a reasonable way that would be a good starting point for drug development. And in this industry, it seems that the number of drugs, the number of molecules that are designed by AI or by machine learning methods and that are now undergoing clinical trials, it grows exponentially. Unfortunately, the time constants in drug development are about 10 years. So if something now enters into clinical trials that was designed by a method that I'm describing here, we will not see it on the market until the next decade. So it's the gratification is not instant, unfortunately. It also costs a few $1 billion to bring drugs to market. But these methods are changing dramatically the way that this entire field looks like. So we are also interested in genetic models. Again, the foundations are the same, so these are also geometric models. Same way as you can now go to ChatGPT and ask to render an image of an astronaut riding a dog on the moon. You can generate a protein that has a certain structure that, for example, inhibits some target, or for example, it has some motif that we know that binds to the target, and then there is a scaffold that we want to diffuse. Graph neural networks were also used for small molecule drugs in a screening pipeline that allowed to discover new antibiotics. So that was the group of Jim Collins at MIT. So he works on antibiotic resistance. So one of the problems with antibiotics is that bacteria that we try to target with them develop antibiotic resistance. So we now have diseases caused by microorganisms that cannot be defeated by anything that we know. So, and the estimate is a few millions of people die out of these diseases. So if this disease becomes more infected, then we have a pandemic that the COVID will seem children game compared to this. So we need new antibiotics, and that's a way of discovering them. So actually they discovered a new class of antibiotics for the first time in the last 40 or 50 years. So, and that was enabled by graph neural networks. So talking about drugs again, so developing new drugs is an expensive business. Instead of developing a new molecule, you can look at how existing drugs that are known to be safe and approved by regulators, by FDA, can be used in combination. So this is called combinatorial therapies or drug repositioning. So you use a drug that, against a new target, maybe in combination with other drugs. And there are many important things that you want to predict computationally, like, for example, side effects. So that was actually a paper also that one of the first users of graph neural networks in these applications by Marinka Ziknik, who is now a faculty at Harvard. So she was trying to predict side effects of binary combinations of drugs when they use these combinational therapies. We have a big collaboration with Mila, with a group of Joshua Baker and a few experimental colleagues, where we try to look at combinatorial treatment against cancer. So again, drug repositioning, and there we actually, the predictions coincided with what was known experimentally. So we found a clinical study that was testing that particular combination of drugs, and it showed efficiency. Now, in my view, this is probably one of the fields where machine learning and these particular methods will probably have the biggest impact. It takes a lot of work. So it's for somebody like myself, a computer scientist, it's very easy, well, I wouldn't say very, because mostly my students do it, but I would say it's easy to develop a machine learning model and make it work on paper, but when it comes to the validation that would satisfy biologists or even clinicians, it's a different level of complexity, and it takes years. So our Nature paper, for example, that appeared last year, it took more than 2 years to do the experimental validation for the computational method that appeared before. So what we probably need to do, and this is actually the focus of the new institute I now head in Austria, is to change the way that we collect experimental data. So data is really crucial for machine learning. You can argue that data is more important than algorithms. And most of the data that we produce nowadays in the scientific fields, in particular in life sciences and biology, is designed by humans for humans. So it's data that was not supposed to be viewed by the machine in most cases. I know that I'm probably painting it with a very wide brush, but if you think of proteins, for example, so the unsung hero of AlphaFold is the PDB, the protein database. It took 50 years to collect, since 1974. It contains about 250,000 structures obtained with X-ray crystallography and cryo. Each such structure could be an entire PhD of a student or a work of an entire lab or an institute, and can cost between tens of thousands to multiple millions of dollars to produce. So the cost of PDB is estimated between $10 to $50 billion. So that's the cost of the data that was a community effort that went into AlphaFold. Now, if we want, everybody now, especially after the Nobel Prizes, is thinking how to make the next AlphaFold, and it's easy to produce a new algorithm that will be smarter and better, right? Again, relatively speaking, because it was quite a remarkably smart algorithm. But very few people are thinking how to produce the next PDB. And we don't have $50 billion, right? Or at least I don't have $50 billion. And probably nobody, no single institution or single lab has it. So it means that we need to revisit completely the way that we produce experimental data. We probably have something like 6 orders of magnitude gap in the cost and the efficiency of the production of the data. We need to get from 50 billions to maybe a few millions, and from 50 years to maybe a few days or a few months or maybe a couple of years. So it means that we need to think of data that is designed not to be viewed by humans. We need data that is done explicitly for the machine and makes sense only in conjunction with appropriate machine learning methods. This is what we call black box data. I think this is one of the directions from which probably breakthroughs will come in this field of AI for life science. And it means that we need to work together with domain experts, with the experimental biologists to design the methods and algorithms together. So this is my take on this field. There are several efforts that go in this direction, including one of the companies I'm involved in called Vant AI. So they're building a special type of drugs called molecular glues. and they have a special experimental technology that produces protein interfaces instead of costing hundreds of thousands of dollars for the cost of a couple of espresso approximately. Also at high throughput, so you can do millions of these in a matter of probably weeks or months. So I guess that's it. I will probably stop here. Let me know if you have any questions.
Hello, my name is Sasan Bhatta. I would like to ask if exploiting the symmetry of the data for making our algorithms faster for learning models, are we losing anything in the process by using the symmetries?
Yeah, so I don't have a one answer that fits all. So it depends on the problem. In some problems, you know a priori that certain symmetries are meaningful, and it makes sense to incorporate them. What it gives you is data efficiency. So we've seen, right? So basically, we've seen that in case when you have symmetries in your label function, basically the label function maps an entire orbit of the group into a single representation. So you need one sample per instead of having all the samples on the orbit. So it can be orders of magnitude, depending, of course, on what kind of group you have. So data efficiency is one thing. In some domains, in some problems, data is cheap, right? So you can collect images more or less infinite, right? Or you can transform images in a certain way doing data augmentation. In some other fields like chemistry or biology, data is very expensive. So the cost of experimental acquisition of the data is not negligible. So therefore, you want to incorporate in your architectures as much as possible. Now, I should say that there is also pragmatic consideration, which is often called the hardware lottery. And this has to do with the fact that it's not necessarily the most correct or mathematically elegant or meaningful algorithm that gets being used and adopted. And this is something that we see again and again in multiple examples. Convolutional neural networks are one example, right? So if you think of applications in images, shifts are just one particular transformation. So images transform in a more complicated way. What is so special about shifts? What is so special about convolutions? So the special thing about convolutions is that you could implement them efficiently on digital signal processors. In the 80s when Lecan was working on it, and later on GPUs. There is nothing special about shifts other than that, right? That's why you can do other architectures, right? So we have the geometric deep learning blueprint. You can do group equivariant convolutions. You can address rotations, translations, reflections. What wins is how efficiently you can implement it on the hardware platform that you have. And this is one of the reasons why transformers are popular. So there is nothing special about transformers. Transformers, as we've seen also in these lectures, are graph neural networks with positional encoding. It's actually ironic that transformers are permutation invariant, and they are used, probably the most famous use of transformers is for NLP problems, where you don't have permutation invariance, right? So the order of words in a sentence matters. The only thing that brings this extra information, that breaks this symmetry, is positional encoding. So the real reason why transformers are popular because they're efficiently implementable on GPUs.
So I would like to continue, like with the advancement in quantum computing, is there any way like we could break into, we could go back to using inefficient algorithms we consider today to make more fruitful results too?
Yeah, so I'm not an expert in quantum computing, so take it with a lot of salt, what I'm saying, but it is also very broad category. So when people talk about quantum computers, it usually encompasses different technologies that have different advantages and limitations, as well as different use cases. So whether it's a general purpose, Turing-complete quantum machines, or is it quantum simulators? So let's say, somebody, myself, who is not an expert, first thing that probably comes to mind when you think of quantum computers is breaking cryptography, right? So, for example, factorization problems. What is more interesting in my view is applying some form of quantum computations, not on classical data, but on quantum data. And this is again problems like drug design, where the molecules are quantum mechanical systems. You want to be able to simulate the systems efficiently. And in my view, basically this is quantum data, right? So you want with quantum data, you don't necessarily need general purpose quantum computing. This is probably where machine learning methods can be used efficiently.
Thank you. We'll only be taking one last question due to time constraints.
Hello, sir. My question is possibly for you. As CNN grows in the importance of AI, what advancement in hardware and software do you foresee being crucial for accelerating GNS in future?
Yeah, good question. So you're asking basically if there is special hardware for graphs. So first of all, there is, or there was. There are several companies that try to build hardware that is more friendly for these kind of applications. One of them was GraphCore, a British startup. So it was underwent a fire sale for less than $500 million a few months ago to I think to SoftBank. So the issue is that it's very difficult to compete with NVIDIA.
Okay, same question, like you said about NVIDIA, and we have been hearing that NVIDIA is launching this AI chip. So, do you have any idea of them managing the large scale of GNNs in their chip, or are GPUs already optimized for this?
Yeah, it's a good question. So it's a combination of optimizing software and hardware. And again, I don't want to speak on behalf of NVIDIA because I don't know exactly what they're doing, but we do collaborate with many people there, so they are always interested in not only what is currently state of the art, but what likely future state of the art will be, to be able to adapt their chips accordingly, right? Because it is a very expensive and very long business to develop new hardware. So it takes probably hundreds of millions in the cost of chip design and then tape out, and then so it takes years. So you see how the machine learning field looks like. So we now have algorithms that didn't exist just a few years ago, right? Or maybe they existed in some form, but maybe the mathematical foundations, like for example, diffusion models, right? So this is very recent. So transformers appeared in 2017, right? So this is very, very recent by any standards. So of course it's very hard to predict what will be the next state of the art, but of course for chip companies they try to do it. Of course they need to cater also to other architectures that are being used, so they need to be backward compatible. So that's why it's a very delicate and very complicated problem. So there are multiple companies, especially startup companies, that, for example, work on chips for efficient inference in LLMs. So once you train your model, you want, for example, to run it on with very good energy efficiency on your smartphone, right? Something like ChatGPT, not to use the cloud. So you want to something that doesn't take a huge amount of power like a GPU. So there is all sorts of hardware considerations and hardware architectures for different use cases, but it's hard to say what is whether there is a single one that is being developed or is going to be. Yeah, so it's a continuously evolving landscape. Yeah, I think I'm being kicked out from the podcast. Yeah, so this is my second time in Nepal. I was already in 2019, 5 years ago, in the second school organized by NAMI, and there I gave just one lecture. Now it's an entire little course that we are teaching. And basically I'm back. I think this was one of the best trips that I had in my life, probably, in 2019, and I like very much Nepal and the place, the people.
it's a little bit hard to say what the students get from the course, but I hear nice, interesting questions. So I hope that at least they will be able to get something, or at least to get an idea about where to look and where to study deeper. I think what is good about the machine learning field and the machine learning community is that there is a lot of material and a lot of open source. So you start with already in a position where it's very easy to ramp up. And it's also a global community. So you can collaborate with other people virtually. You don't necessarily need to be elsewhere. So same way as I can do my work in Oxford, I presume I can do it here. So at least to some extent. So I think that's good, and I think NAMI is really opening up these possibilities, or maybe showing that what can be done and what exists elsewhere, what is the state of the art to people in Nepal, and I think it encourages the students, so it prepares them, but also probably inspires them to pursue opportunities in this field.